This is the Chem 1 video for VSEPR, Valence Shell Electron Pair Repulsion Theory. So in the last unit you learned how to draw Lewis structures. If I give you the formula, you put the first atom in the center, you put all the other atoms around it, you draw your bonds, you draw your lone pairs, which was a really good representation of any molecule in a two-dimensional way. The thing is, in reality, those molecules are not in 2 dimensions, they're in 3 dimensions, so they're not flat. They're coming in and out of the page. So because molecules come in these 3-dimensional shapes, we had to create some kind of theory or some kind of idea to help us classify all of the different potential 3-dimensional shapes that molecules can come in. Before we really get into the nitty-gritty of how we come up with those shapes and how we determine bonds and lone pairs, that kind of thing, try to go through the first page of the notes by yourself, questions 1 through 6, using those top 2 models as an idea. That first model on the left, CH2O, has 3 areas of bonding electron density and 0 areas of non-bonding electron density for a total of 3 areas. The one next to it, NH3, has a total of 3 areas of bonding electron density, 1 area of non-bonding electron density, and 4 total areas. So 3 plus 1 is 4. Using those 2 models, see if you can answer questions 1 through 6 on your own. I'll give you a little bit of time. Pause the video here. Work your way through those questions, or at least attempt to, and then we'll pick up with those questions here in just a second. Hopefully now you've answered, or at least attempted, the questions for 1 through 6. We're going to run through it here very quickly just so that we can make sure we're all on the same page. First off, what does a solid line between 2 different element symbols mean in our models? Well, remember, a solid line will always represent a bond, and pairs of dots represent lone pairs. We learned that in Unit 6. Still true now. It wants us to circle or highlight the areas of electron density for those 2 molecules. Well, let's look at that first model, that first molecule on the left. 3 areas of bonding. Well, there's 1 area of bonding. Oh, let's get a different thing. There we go. That's going to be a little bit better. There's 1 area of bonding. Here's a second area of bonding. There's a third area of bonding. Those areas between the C central atom and the H's and the O. We do not count the lone pairs or any electrons on any of the outer elements. We only are looking at the center atom to determine areas of electron density. On that second molecule, we have 1, 2, 3 areas of electron density. But we also have 1 area that is not bonding. Again, we are only looking at those center atoms. That's what's going to do a lot of our heavy lifting for the shape. One quick little note, let's look right there. Even though that is a double bond between the C and the O, it only counts as 1 area of electron density, so please make sure you keep that in mind. So we've circled or highlighted areas of electron density. When determining the number of areas of electron density in a Lewis structure, which do we count? Well, we count bonds on the center atom. We count lone pairs on the center atom. We do not care about the total number of atoms. We do not care about lone pairs on the outside atoms. That center atom is going to determine most of the traits and facts about our molecule. All right, when determining the number of areas of electron density, do I count double bonds as 1 or 2 electron dense areas? We answered that earlier. We count it as 1 area of electron density. Again, here's our example, that first model. There's only 3 areas. So that tells us that because there's only 1, 2, 3 areas, even though there is a single and double bonds, it doesn't matter the number of bonds. They are in their own separate area. They are only 1 area of density. Explain the difference between area of bonding, electron density, and non-bonding. Well, I mean, one has bonds and the other one doesn't. So remember, bonding is when I have electrons shared, and then when I have a non-bonding, that's going to be my unshared electrons. So make sure you remember the definition of bonding and not bonding, or non-bonded, back from Unit 6. Lastly, circle the correct word or phrase to complete sentences. Pairs of electrons will repel, right? Pairs of electrons are both negative. Negative and negative is a repelling force. Two bonds on the same atom will try to get as far from each other as possible. That's kind of a continuation of A. If you have two positive magnets and you put them near each other, they're going to push each other away so they can be as far from each other as possible. Last but not least, a lone pair of electrons and a bonded pair of electrons will push away from each other. Same thing. One might be shared and one might not be shared, but they're still negative at the end of the day. It's just like, oh, hey, I have two negative magnets. Whether I'm going to keep that negative magnet or share it with another person doesn't really matter. They're still negative magnets. They're still going to repel each other. Which brings us to VSEPR theory, valence shell electron pair repulsion. It is this idea that because all electrons are negative, all electrons will push against each other. They're going to fight each other. And because there's this pushing from all of the electrons involved, it's going to move atoms around your molecule. So we don't have to do any calculations. You will never have to do it, but calculations at one point were done to kind of determine sometimes electrons push more, sometimes they push less. But the big idea here is that electrons are going to push each other away so that they are at the most stable, farthest away distance possible. Just as a heads up, we're going to need to be working kind of in three-dimensional here. We have some 3D models in the classroom that you can have full access to kind of help you get your mind around these different shapes. We are working on a paper. Paper is 2D, so you're going to have to use a little bit of imagination to try to imagine what some of these 3D shapes might just look like. But we'll do our best. So in order to use this VSEPR theory, in order to figure out the shapes and figure out how electrons are pushing away, the first thing you have to do is draw your Lewis structure. You have to draw your Lewis structure. You don't have an option. Otherwise, you're going to miss lone pairs. You're going to miss double bonds. You're going to miss single bonds. You're not going to be able to figure out the areas of electron density, all of that good stuff. So you have to be able to draw the Lewis structures for your molecules. Once you've drawn your Lewis structure, then you can look at the center atom to help you determine the number of areas of electron density. And once you've determined the total number of areas of electron density, that will tell you the number of lone pairs or unbonded areas and the number of bonded areas. So here are the shapes that you have to memorize. We will not give these to you. You have to memorize these. Okay? So if you have an area or you have a molecule with two areas of electron density, and both of those are bonded, in other words, no lone pairs, that's going to be a linear shape. The electrons are going to push each other far enough away so that they can be the maximum 180 degree apart, kind of around the circle. They're going to be at opposite ends. It's like the North Pole and the South Poles, as far away on the planet as you can possibly get. So two areas of electron density with no lone pairs, that's linear. If you have three areas of electron density with no lone pairs, then when they start spreading out, your electrons are going to push and push and push and push and push. These two pairs will get away from each other, but there's also this other pair over on the right side, and it's going to be pushing against both of those as well, which means the maximum distance you can kind of get apart from each other is 120 degrees. So think about it like a circle, full 360, divide that up by 3, you end up with 120, 120, and 120. That's what you see. So trigonal planar, it's essentially a flat molecule where the atoms are 120 degrees apart. If one of your three areas is a lone pair, we say that that shape is bent or angular. You can use either one, memorize one of them. You don't have to memorize exactly what the angle is on that bond, but know that it's less than 120 degrees for a really simple reason. Lone pairs can spread out more than bonded pairs. So this lone pair at the top will end up actually spreading out farther than these two bonds down here. So because this lone pair on top will spread out farther, it forces these bottom two pairs to squeeze together just a little bit. Not a ton, but there is a few degrees difference there. Again, you don't have to memorize that it's less than 120 or what the exact value is, or well, you do need to just remember that it is less than 120. You don't have to memorize exactly what it is. I think it's like 117.5, not important, just know that it's less than 120. Moving on to 4 areas of electron density. If it is 4 areas of electron density with no lone pairs, then we get a tetrahedral shape. This is the weird one. Here's where having a model or kind of having a really good sense of imagination is very helpful. Because what you all always want to do is say, oh, well, there's my triangle, divide it into 4, that's 90 degrees. Here's the thing, that's true if you were only working in 2 dimensions. We're working in a 3rd dimension. So there's kind of this twist where the molecule actually comes out and into and out of the page. This guy, this little atom, comes out of the page, that one goes into the page. So it's, if you kind of want to imagine that 90 degrees, that's okay as a starting point, but then you got to imagine a little twist in it, which gives us this angle measure of 109 degrees. Similarly to trigonal, planar, and bent or angular. For the record, we call that one a tetrahedral. When I remove one of those atoms and replace it with a lone pair, it forces all of those bonds to squeeze together just a little bit more. This lone pair on top spreads out, and you get what we call the trigonal pyramidal, or trigonal pyramid. It has a bond angle of less than 109. You don't have to know exactly what it is, but know that it's less than 109. If I replace 2 of those atoms with lone pairs, well, these are going to spread out pretty far, and these are going to spread out as far as possible, which is going to force the remaining bonds down here at the bottom to squeeze even closer together. It's a repeat. We say that this one is also bent or angular. Again, just memorize one, that's fine. But know that it is way less than 109 degrees. That's why there's 2 of those less than symbols. So you need to know these shapes, you need to know the different combinations, the areas to lone pairs, you need to be able to name shapes like this, and you have to be able to remember these bond angles. So 180, 120, 109, less than 120, less than 109, and way less than 109. Basically match the degree to the shape and be able to classify different molecules. We said this in the long explanation on that last slide, but remember that lone pairs will always repel more than the electrons that are stuck together in a bond. There's more freedom for the lone pair to spread out because it doesn't quite have the same restrictions. So imagine for a lone pair, it can pretty much fit anywhere it wants to go as long as it's still pretty much shared with that nitrogen. Meanwhile, if I have a lone pair electron, it has to stay between those 2 molecules, between the center and between the center atom and the outside atom. So it has less freedom, and because it has less freedom, it ends up being squished while the lone pairs can really spread out. Here's another way for you to remember, instead of looking at total areas of electron density and then figuring out how many lone pairs you have. This table will tell you essentially the entire same thing, but just comparing areas of bonded electron density to areas of non-bonded electron density. So the big table that we spent a lot of time on shows total versus lone pairs. This table shows you bonds versus lone pairs. Memorize one of the two tables. It doesn't matter. You can use either one equally. Use the one that makes more sense to you, and you'll be able to do it pretty well. We're going to get a lot of practice classifying. So if we're still kind of a little unsure of how this works, that's okay. We will work through it. So we're actually going to run through all 6 examples so you can kind of see very quickly how we can classify molecules. First off, I have CO2. I have it drawn here already. You would have to draw it yourself on an exam or on a learning check or on a homework. So here's my CO2. We can look at the center atom and see that I have 1 area of electron density, 2 areas of electron density. So 2 total areas. 2 of them are bonding, right, because they have bonds in them. No lone pairs. And if I use that first table, this combination of 2 total with no lone pairs spits out the linear result. If I want to use the table we saw most recently, comparing bonds to lone pairs, well, I have 2 bonds, 2 links, no lone pairs. That still spits out linear. So you can pretty easily see you can either calculate total versus lone pairs or links versus lone pairs and be able to spit out the same shape. We would say that the CO2 molecule is linear. Anytime you only have two atoms, so like O2 right here, you got O1 and O2, there's 1 area of electron density. You really can't use the table to determine what the shape is going to be, which means for us, for simplicity's sake, we're always going to say that a diatomic compound, so O2, Cl2, or any other thing that only has 1 area of electron density, like that, is going to be linear. So 2 atoms, always going to be linear. All right, here's BH3. We look at the center atom. We got B. We got 1 area, 2 area, 3 areas total. And of those 3 areas, 3 are bonding. And none of them are lone pairs. So if we look at that first table at the beginning of our video, or on the first page of our notes, second page of our notes, sorry, this 3 total with no lone pairs spits out the trigonal planar result. If we want to use that other shorter table, we say that, oh, look, there's 3 links, 3 areas of bonding. None of those areas, or none of the areas have lone pairs in them, so no lone pairs. That still spits out a trigonal planar result. Again, it doesn't matter which table you use, you're going to get the same answer. Here's an example of NO2 minus. So we have our N in the center, we have 2 O's attached to it, we have 1 area, 2 area, 3 areas total. 2 of those areas have bonds, and 1 of them has a lone pair in it. So if I look at the chart, 3 total with 1 lone pair, that spits out a bent or an angular shape. Either one will work. If I want to use the other table, 2 areas of links, right? 2 of my areas have bonds in them. Remember, even though there's a double bond in that 1 area, it still only counts as 1 area, with 1 area of lone pair. So that still spits out the bent or angular response. All right, let's look at H2O, a pretty common molecule. We have 1, 2, 3, 4 areas total. I know it's a little weird that we say, oh, well, single and double bonds count as only 1, but each set of lone pairs gets their own. It's a pretty simple reason. Remember, lone pairs can spread out a lot more than bonds can. So the lone pairs can actually get far enough away to each have their own area. But remember, bonds have to stay between those 2 atoms, so they can't really get away. So single double bonds still only count as 1 area, but every single bit of lone pair on the center atom gets its own area. So I have 4 total areas, 2 with bonds. There we go, 2 bonds. 2 with lone pairs, right? There's my bonds. There's my lone pairs. So look at the big chart. 4 areas total with 2 lone pairs gives me the bent or angular response. If I use the short table, 2 links, 2 lone pairs, still spits out bent. CF4, these are always kind of nice and quick and easy. 1, 2, 3, 4. 4 links, no lone pairs. 4 total, that's going to be your tetrahedral. Anytime that you have a single atom in the center with 4 things around it, it's going to be tetrahedral 100% of the time. If there are 4 atoms attached to a center atom, it's going to end up being tetrahedral for us. NH3, you have right there, is going to be trigonal pyramidal. It's got 1, 2, 3, 4 areas total. So 4 total areas. It has 3 areas with links, 1 with lone pair. So whichever table you use gets you a trigonal pyramidal response. So now we've seen all of the different shapes kind of all in action. We've done it from molecule through one of our tables to get to the shape. Now we're going to do the whole thing. So we have pH 3. Before we're able to effectively classify it, tell us what the shape is, we have to be able to draw it. So go ahead, pause the video here, take the chance to go and keep practicing your nassling, draw out the shape, and in a few seconds it'll pop up with all the work, and we'll start talking about how to classify the shape. Okay, so here we go. Here's all of our work. 3 bonds, 1 lone pair, so then we can start drawing our molecule. We got a P with 3 H's. Each of them have 1 bond. There's our 3 bonds, and 1 lone pair. We're good and happy. So let's look at our areas. We have 1, 2, 3, 4 total areas. We have 1, 2, 3 that are bonded, 1 with lone pairs in it. So if I go to my table, that's going to tell me that this is trigonal pyramidal. Either one of those tables will spit out that result. Either 4 total with 1 lone pair or 3 bonding with 1 lone pair. You need one of the tables, just memorize one of them. Either one will get you the final answer. Here's another example, CCl4, same deal as with number 1. Pause the video here, take some time to work through the problem, and then we'll pop back up in a few seconds, and we'll go through finding the shape. Alright, here we go. Here's our work. 40 electrons needed, 32 available, 4 bonds, 12 lone pairs, so we can start drawing our molecule. Start with our C in the center. We arrange our CLs around it. Everything gets 1. Oh hey, we've used all 12 or all 4 of our bonds. Start giving out lone pairs. Alright, CL now has 8. This CL now has 8. The bottom CL has 8. That CL has 8. Let's make sure we've used all our lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've used all of our lone pairs, which means the carbon in the center doesn't get any. So now we can safely say we have our molecule drawn. Let's count our areas. 1, 2, 3, 4 areas total. All of them are bonding. None of them are lone pairs, so either 4 bonded with no lone pairs or 4 total with no lone pairs will give you that tetrahedral shape. Notice there's not a whole lot of work between getting the molecule and getting the shape. You just have to have that table in your head ready to go. Alright, last example, ClO2 with a -1 overall charge. Same deal again. Pause the video. Try to get the work out first. We'll come back in just a second. We'll draw it. We'll talk about what the shape is going to look like. All right, here's our work. It could be a little bit cleaner, but you know, working with a stylus is sometimes the easiest thing in the world. So 2 bonds, 8 lone pairs. Don't forget that extra -1 charge, giving you the extra electron in your available step. And we can start drawing it. Cl is the first thing, so that's going to go in the center. I have two bonds and 8 lone pairs. Everything gets 1. Then I go in and start making sure that everybody has 8, so that our octet rule is good and happy. And because, remember, it's an ion, we give it its overall brackets. So, now we have our molecule drawn. I have 1, 2, 3, 4 areas of electron density total. 2 of them are bonds, 2 of them are lone pairs. So let's write that all down. 2 total, 2 areas of bonds, 2 bonds, 2 lone pairs. So if you look at one of your tables, you should see my shape is bent. Even though it looks like Mr. Flato drew our shape as a linear molecule, you can't always trust how it's drawn. I promise you right now, we will pick some pictures that might look like they're linear or might look like they're flat, but when you actually get the shape, it's not linear. They're not trigonal planar. They're supposed to be pyramidal, or they're going to be bent like this one. So always rely on your tables before you rely on your eyes. Sometimes it is linear, other times it's not. Make sure you have one of those 2 tables in your head. If that's really all it comes down to when it comes down to shape, is you have to know the molecule and connect it to one of your tables. If you're having trouble seeing how the calculation or the counting of the area of electron densities, and how do I know whether they're bonded or unbonded or linked or unlinked, come talk to us. We will go through every single practice problem possible. We can just make up a bunch of molecules for you. If you want even more practice, go back to the old Unit 6 problems where you drew molecule after molecule, and just go back and start practicing identifying their shapes too. We're happy to check it if you come bring it into us. Other than that, keep practicing, and you'll be great at this in no time.